Hi, in this video, we are going to see Rolle's theorem. How Rolle's theorem can be applied for a function. Okay, let's consider a function f of x on the closed interval a comma b. That is, x belongs to this interval. So x can be any value from a to b. Okay, so how Rolle's theorem can be applied for this function f of x over the closed interval a comma b. So if I want to apply Rolle's theorem for any function, say f of x, so the function, the f of x has to meet the three conditions of the Rolle's theorem. So the first condition is f of x, the given function, has to be continuous and also the defined on the closed interval a comma b. So the word defined is not there, we can include it. So f of x, the given function f of x, has to be defined and continuous on the closed interval a comma b. And also the second condition is the function f of x has to be differentiable on the open interval a comma b. So I hope you are aware of what is closed interval, what is open interval. For example, if x belongs to this closed interval a comma b, that is, we'll have a square bracket over here, then we can include both the values a and b. The boundary values can be included for x, that is a less than or equal to x less than or equal to b. So if x belongs to the open interval a comma b, then the boundary values cannot be included. Any value between them can be included. We can write this one as an inequality a less than x less than b. So the first two conditions are, the first condition is the given function f of x has to be defined and continuous on the closed interval a comma b, and the given function f of x has to be differentiable on the open interval a comma b. And the third condition is f of a and f of b must be equal. That is, I'm going to plug in the boundary values a and b into the given function f of x. So when I plug in x is equal to a, I'm getting f of a. When I plug in x is equal to b into the given function, I'm getting f of b. So they must be equal. So actually f of a and f of b are the values of y. That is, f of a is the value of y when I plug in x, when x is equal to a, and f of b is the value of y when x is equal to b. So the values of y must be equal when x is equal to a and x is equal to b. So if your function meets all the three conditions which I've explained so far, then we can say the Rolle's theorem can be applied for that function. Okay, so now it's very clear for which type of functions we can apply Rolle's theorem. So whenever a function meets the three conditions given over here, then Rolle's theorem can be applied for that function. So what can I do if I apply Rolle's theorem for that function? I'll be able to find a value of x, that is x is equal to c on the open interval. That means x is equal to, I find a value for x, it is say c, that belongs to the open interval a comma b. That means a comma b means the c can be any value between a and b. So I will be able to find a value for x, that is c, between a and b, so that f prime of c is equal to 0. So this is the ultimate aim of Rolle's theorem. So that is, we are aiming to find a value for x, say c, between the two values we have in the given interval, so that f prime of c is equal to 0. So for that, the function has to meet the three conditions of Rolle's theorem. Okay, here, the next question, what we have over here is, what do we have to find this value c using Rolle's theorem? So if f of x is a given function, already we know, 1 second, f of x is a given function. If I find the first derivative of this function, then I'll be getting f prime of x. So what does this f prime of x represent? So this is the slope of the tangent line to the graph of f of x. F prime of x represents slope of tangent line. Okay, so for any line, if the slope is equal to 0, how the line can be? It will be an horizontal line. So whenever the slope of a straight line is 0, then it will be an horizontal line. So here, f prime of c is equal to 0. That means the slope of the tangent line at x is equal to c equals to 0. That means we'll have a tangent line which is horizontal at x is equal to c. So we have a function, it meets all the three conditions of Rolle's theorem. I just want to find the value of x between the two boundary values a and b at where the tangent line is horizontal. I just want to find the value of x between a and b. So at that particular value of x, the tangent line is horizontal. What is that value of x? So we have to find the value of x. So that is the ultimate aim of using Rolle's theorem, to find the value of x where the tangent line is horizontal. Okay, to have better understanding on Rolle's theorem, we can interpret the Rolle's theorem geometrically. So for that, we can go to the graph of the function f of x. Okay, let me go to the graph of f of x. So here we have a graph, and we can, this is a graph of f of x. Okay, if I want to apply Rolle's theorem for this graph, as I told you already, it has to meet the three conditions of Rolle's theorem. The first condition is the graph has to be defined and continuous on the closed interval a comma b. That is, from a to b, the graph has to be defined and continuous. So clearly, this graph is defined and continuous over the closed interval a comma b. That is from a to b. So look at here. There is no horizontal asymptote, there is no hole, anything. So there is a smooth curve from x is equal to a to b. So from this, we can decide that the graph is defined and continuous on the closed interval a comma b. So now our next challenge is, so whether this function, I mean the graph, is differentiable over the open interval a comma b. So if it is f of x, we can find the first derivative, and we can check for any value of x between a and b if f of x is undefined, or it is defined for all the values of x between a and b. But here there is no function, we have the graph. How to find, I mean how to determine? So if the graph of f of x is differentiable over the open interval a comma b. Okay, so for that, we can look at the another graph to understand this stuff. That is whether a graph is differentiable on the open interval a comma b. Okay, let me go to the other graph 1 second. Here we have another graph. When I look at this graph carefully, there is a sharp corner at x is equal to 1. Did you notice that? Sharp corner means there is a sudden change at x is equal to 1. So because when I look at the graph on the left side of x is equal to 1, there is a smooth curve. On the right side of x is equal to 1, there is a straight line. So whenever there is a sudden change in a graph at a particular value of x, so then you'll have a sharp corner like this on the graph. At this sharp corner, we'll not be able to define the first derivative. That is f prime of x is not f prime of x is cannot be defined at x is equal to 1. So we have to say the function, I mean, for example, if f of x represents this graph, then f of x is not differentiable at x is equal to 1. So because we have a sharp corner at x is equal to 1, we'll not be able to define the first derivative. So f of x is not differentiable. I mean, the given graph is not differentiable at x is equal to 1. So for any graph, if I want to check if it is differentiable or not, I have to see whether there is any sharp corner in the given graph. Okay, now let's go to our original graph. 1 second. Here in our graph, there is no sharp corner like what we have discussed in the previous graph. So from A to B, there is a smooth curve over here. So the graph is differentiable over the open interval A comma B. So the second condition of Rolle's theorem is met by the graph. Now we have to check the third condition of Rolle's theorem. So that is f of A and f of B must be equal. That is the value of y when x is equal to A, the value of y when x is equal to B must be same. Okay, now let me draw an horizontal line we have over here. Say the value of y at this particular point on the y-axis is k. So what is the value of y when x is equal to a on the graph? When x is equal to a, the value of y is k. That is, the point is a comma k. What is the value of y when x is equal to b on the graph? So that is also k. So we have the point b comma k on the graph. So when x is equal to a, the value of y on the given graph is k. So we have the point a comma k on the graph. When x is equal to b, again we have the same value for y. That is k. So we have the point b comma k on the graph. So the value of y at x is equal to a, the value of y at x is equal to b are equal. Or in other words, f of a equals to f of b. So the given graph meets the third condition of Rolle's theorem. So the graph we have over here meets all the three conditions of Rolle's theorem. So we can apply Rolle's theorem over here. So that is, we'll be able to find a value for x between a and b, say x is equal to c. So we can find the value of x, that is x is equal to c, between a and b at where the tangent line has to be horizontal. Clearly at x is equal to c, the tangent line is horizontal over here. Since the tangent line is horizontal, the slope of the tangent line, which is given by f prime of x at c, So the slope of the tangent line C means you have to replace this x by c. So f prime of c says the slope of the tangent line at x is equal to c must be 0 because the tangent line is horizontal. So I think now everyone can understand Rolle's theorem geometrically. So our aim is to find value for x between a and b at where the tangent line is horizontal. Then the slope of the tangent line, that is the first derivative of the given function, will be equal to 0. So the first derivative of the given function is given by f prime of x. When I plug in x is equal to c, then I'll be getting f prime of c. It has to be 0. That means the slope of the tangent line at c equal to 0. Then the tangent line is horizontal. Okay, let's consider another graph for the same Rolle's theorem. Just a moment, let me go to the second graph. Okay, look at the graph over here. So the same thing, what we have discussed for the first graph, that is, 1 second, yeah. So here, first we have to check the first condition of the Rolle's theorem, that is, the function has to be defined and continuous on the closed interval a comma b, from a to b. So clearly the function is defined and continuous from x is equal to a to x is equal to b. So the first condition of Rolle's theorem is met. Okay, the second condition is the function, I mean the graph has to be differentiable over the open interval a comma b. So there is no sharp corner, as I explained in one of the graphs previously. There is no sharp corner, something like this. There is no sharp corner for this graph at anywhere. So the given graph is differentiable on the open interval a comma b. So the given graph meets the second condition of Rolle's theorem. Okay, now the third condition is f of a and f of b must be equal. It is the value we have when x is equal to a, the value of y when x is equal to a, the value of y when x is equal to b must be same. Okay, we can check that by drawing an horizontal line as we have done in the previous graph. Let me draw an horizontal line over here. Okay, look at here. Let's say at this point on the y-axis, we have the value of y as k. So at x is equal to a, on the graph, the value of y is k. So I have the point a comma a, k. And at x is equal to b, the value of y on the graph is k, the same value. So we have the point b comma k. So when x is equal to a and when x is equal to b, we have the same value for y on the graphs. So f of a and f of b are equal. So the given graph meets all the three conditions of Rolle's theorem. So we'll be able to find a value, say c, between a and b at where the tangent line is horizontal. That means tangent line is horizontal means the slope of the tangent line given by f prime of x. So here x is replaced by c. So this is the slope of the tangent line at x is equal to c will be 0. So because the tangent has to be horizontal. Okay, so here we can draw two tangents between a and b to the graph of x. So where both the tangent line is horizontal. Both the tangent lines are horizontal. So in this case, so here between a and b, we'll be able to find two values for x, c1 and c2. These two values, the tangent lines we draw for the graph of f of x are horizontal. So in this case, if we equate f prime of c is equal to 0, you'll be getting two values for x. X is equal to c1 and x is equal to c2. So it is not like the previous one that is always will be getting only one value between a and b at where the tangent line is horizontal. It is not like that. Sometimes you'll be getting two values between a and b. You'll be getting two values for x between a and b. At those two values of x, the tangent line will be horizontal. Okay, let's look at one more graph to have better understanding on this one. Just a moment. Here we have another graph. So the same thing, we have to check all the three conditions of Rolle's theorem for this graph. So from x is equal to a to x is equal to b. So clearly the graph is defined and continuous. And also there is no sharp corner on this graph. So the function is differentiable over the open interval a comma b. And also we can draw an horizontal line to check whether we get the same value for y when x is equal to a and x is equal to b. So clearly we get the same value for y. For example, if I assume the value of y is k at this particular point on the y-axis. So when x is equal to a, I get y is equal to k on the graph. When x is equal to b, I get the same value for y, that is k. So for x is equal to a and x is equal to b, I get the same value for y, that is f of a equals to f of b. So the graph we have over here meets all the three conditions of Rolle's theorem. So definitely there must be a value for x between a and b at where the tangent line has to be horizontal. So here we have a value c between a and b at the point, I mean, at x is equal to c, the tangent line is horizontal. So the slope of the tangent line at c must be 0. Okay, I think everyone can understand so the Rolle's theorem, what I've explained so far. So now let's look at some examples. Sample problems, how to find value of c between a and b using Rolle's theorem. Okay, let me go to the first example. Let's consider the function f of x equals to x squared positive 4x positive 5 over the interval negative 3 comma negative 1. So here we have to use Rolle's theorem to find a value of x between negative 3 and negative 1, where the tangent line to this curve will be horizontal. Okay, now so to do that, we have to check the three conditions of the Rolle's theorem for this function. So it's a regular polynomial function, so it's continuous for all real values of x. So the given function is defined and continuous on the closed interval negative 3 comma negative 1. So the first condition of the Rolle's theorem is met, and the second condition is we have to check this function is differentiable over the open interval negative 3 comma negative 1. So what if if I find the first derivative of this function? So the derivative of x square with respect to x is 2x, and the derivative of 4x is just 4, and the derivative of this constant is 0. So f prime of x is defined. The f prime of x for 2x positive 4 is defined for all real values of x. So this 2x positive 4 is defined for any value between negative 3 and negative 1. I mean, on the open interval negative 3 comma negative 1. So clearly this function is differentiable on the open interval negative 3 comma negative 1. So the second condition of Rolle's theorem is also met. Now let's take the third condition. That is, we have to find the value of the given function f of x at x is equal to negative 3 and x is equal to negative 1, and they must be equal. Let's do that. So now I'm going to plug in x is equal to negative 3 into the given function. So f of negative 3 equals to negative 3 whole to the second power positive 4 times negative 3 positive 5. And let's simplify this. F of negative 3 equals to, so the f of negative 3 to the second power will be 9, positive times negative will be negative 12, positive 5. So f of negative 3 equals to 9 positive 5 will be 14, 14 negative 12 will be 2. Okay, now let's plug in the second boundary value of the interval negative 1 into the given function. So then we get f of negative 1 equals to negative 1 whole to the second power positive 4 times negative 1 positive 5. Okay, f of negative 1. So negative 1 whole to the second power will become just 1. Positive times negative will become negative 4 positive 5. So f of negative 1 equals to 1 positive 5 is 6, 6 negative 4 is 2. So f of negative 3 equals to f of 1. I mean f of negative 1. So the given function f of x equals to x squared positive 4x positive 5 meets all the three conditions of Rolle's theorem. So since the given function meets all the three conditions of Rolle's theorem, we will be able to get a value of x between negative 3 and negative 1 at where the tangent line to this curve will be horizontal. Okay, let's do that. Just a second. Okay, already got the first derivative of f of x, that is f prime of x. Now I'm going to replace this x by c. So on the right side also I have to replace x by c. So I get f prime of c is equal to 2c positive 4. So we have to get the value of c so that f prime of c equals to 0. So here we equate the first derivative at c equals to 0. So that means that the slope of the tangent line at c equals to 0. That is the tangent line is horizontal. So now we are going to get a value c. We are going to get a value for c between negative 3 and negative 1 at where the tangent line will be horizontal, because the slope at the value c equals to 0. The slope of the tangent line at c is equal to 0. Okay, now we can, what do we know for f prime of c? We know that f prime of c is equal to 2c positive 4. So we can plug in this 2c positive 4 for f prime of c. So I get 2c positive 4 equals to 0. Now I have to solve for c. So I subtract negative 4 from both sides. So I get 2c equals to negative 4. Then I divide both sides by 2. So 2 will cancel out. Negative 4 divided by 2 is negative 2. So which is in the open interval negative 3 comma negative 1. So this is the value of c which satisfies the Rolle's theorem. That is if I draw a tangent line to this curve, f of x equal to x square positive 4x positive 5 at x is equal to -2, that tangent line will be horizontal. Okay, let's look at another example. Consider the function we have over here, that is f of x equals to x to the third power -3x positive 3, where the closed interval 0, 1. Okay, now so I have to find the value of x between 0 and 1. So where the tangent line to this curve will be horizontal. So using Rolle's theorem. So first I need to check all the three conditions of the Rolle's theorem. So it's a polynomial function. So it is defined for and continuous for all real values of x. So the given function has to be defined and continuous on the closed interval 0, 1. And also, if I find the first derivative of this function, I'll be getting 3x to the second power -3. Okay, here, so this is again, the derivative is also a polynomial. So it is defined for all real values of x. So it is defined on the closed interval 0, 1. So the two conditions of Rolle's theorem are met. Now we have to check the third condition. That is, we have to plug in the boundary value 0 and 1 into the given function. Okay, let's do that. Okay, so first let me plug in the first value of first boundary value of x, that is 0, into the given function. F of 0 is equal to 0 to the third power, -3 times 0, positive 3. I get f of 0 equals to 0, -0, and second, positive 3. So finally, I get f of 0 is equal to 3. Okay, now let me plug in the second boundary value 1 for x into the given function. So f of 1 equals to 1 to the third power, -3 times 1, positive 3. So f of 1 is equal to 1, -3, positive 3. This one will cancel out. F of 1 equals to 1. So here, f of 0 and f of 1 are not equal. We get different values for f of 0 and f of 1. So the third condition of the Rolle's theorem is not met. So the Rolle's theorem does not hold for the given function. Okay, let's look at one more example. Okay, consider the function f of x equals to tan x over the closed interval 0, pi. Okay, so here the same thing what we have done in the previous problems, that is we have to find the value of x between 0 and pi. So where the tangent line to this curve will be horizontal. So we can use Rolle's theorem. So for that we have to check whether the given function meets all the three conditions of Rolle's theorem. Okay, so let's check the first condition. That is, the given function has to be defined and continuous over the given closed interval, that is 0, pi. So here f of x equals to tan x, and there is a value in the closed interval pi over 2. So because before 0 and pi, we know that there is a value pi over 2, that is 90 degree. When I plug in this value pi over 2 for x, with this one, it will become tan pi over 2. We know very well that tan pi over 2 or tan 90 degree is undefined. So for one of the values in the given closed interval, the given function is not defined. So what we need to conclude is the given function is not defined on the closed interval 0, pi. So the first condition, even the first condition of Rolle's theorem is not met. So we don't have to proceed this problem further. So the Rolle's theorem does not hold for this function. Okay, let's do one more example. Consider the absolute value function we have over here. That is f of x equals to absolute value of x over the closed interval -1, 1. Okay, the same thing. That is, we have to find a value for x between -1 and +1 at where the tangent line to the curve f of x equal to absolute value of x is horizontal. Okay, so we can use Rolle's theorem. So for that, we have to check all the three conditions of Rolle's theorem for this function. So here, the first condition is the given function has to be defined and continuous on the closed interval -1, 1. So here we don't find any denominator, particularly we don't find any variable in denominator. So this function is defined for all real values of x. So whatever value we plug in from -1 to 1 for x, it will be defined and continuous. So the given function is continuous, defined and continuous on the closed interval -1, 1. So the first condition of the Rolle's theorem is met. Okay, now let's check the second condition. So to check the second condition, we have to find the derivative of the given function. So it's an absolute value function. First, we have to be knowing how to find the derivative of an absolute value function. Okay, let's consider an absolute value function f of x equals to absolute value of u. So assume u is a function of x. Okay, to get derivative of this absolute value function, so in the first step, whatever stuff I have inside the absolute value, that should be taken as it is without absolute value. In denominator, this stuff should be taken, the given function on the right side of the given function should be taken as it is in a denominator along with absolute value. So first, again, let me tell you the steps. The first step of finding derivative of absolute value function is the stuff we have inside the absolute value should be taken in numerator, and this stuff should be taken in denominator. This should, the absolute value of u should be taken as it is. So further, I have to find the derivative of the stuff inside the absolute value over here, that is u prime. Okay, now let's apply this procedure in our function. So let's find the derivative of the given function. So f prime of x equals to, so the stuff inside the absolute value should be taken as it is in numerator, and this stuff should be taken as it is in denominator. So further, I have to find the derivative of the stuff inside the absolute value with respect to x. So we have x inside the absolute value. I have to find the derivative of that one with respect to x. So f prime of x equals to x over absolute value of x, and the derivative of x with respect to x is just 1. So f prime of x equals to x over absolute value of x. So x times 1 is x. Okay, now we have to check this first derivative is defined on the closed interval -1, 1. So any value, if I plug in any value between -1 and 1 for x into this function, it has to be defined. So between -1 and 1, we know very well there is a value 0. So if I plug in this value 0 into this first derivative, what will happen? So the denominator will become 0 because we have the variable x in denominator. So when I plug in x is equal to 0, then it will be absolute value of 0. That's nothing but 0. So in a fraction, if the denominator is 0, it is considered to be undefined. So clearly, the first derivative is not defined on the open interval -1, 1. So because for a particular value 0 between -1 and 1, the first derivative f prime of x is not defined. So the given function is not differentiable on the open interval -1, 1. So the given function does not meet the second condition of Rolle's theorem. So we don't have to proceed further. So the Rolle's theorem does not hold for the given function.